So we're going to continue doing work in section 3.1. The other day we introduced a method by which we can calculate the slope of a tangent line. That was through limits. And then we generalized that to calculate the derivative function. So the derivative function can be calculated through this limit. The limit as h approaches 0 of f of x plus h minus f of x over h. Now, when we were calculating this the other day, I did this calculation with 4 steps. You don't have to do it the way I do it. It's just a suggestion. Kind of organizes things, gives you a nice, neat path to work your way through it, but you don't have to do it the way I do it. This is going to be f prime of x. And f prime of x is going to measure the slope of the tangent line anywhere for your function. So, measures the slope of the tangent line at any value of x. So if you want to know the slope of the tangent line to your function f at any particular point, you can plug in that value of x into its derivative function and find the slope of the tangent line. That's going to tell you how the function is changing at an instant. Let's practice using that one more time with problem number 66, and then think a little bit more about the definition and what it actually means relative to a graph. 66 has g of x equals x squared minus x, and eventually we want to find the derivative and then the value of the derivative at c equals 1. But let's find the derivative first based on this definition. My first step in that is going to be to calculate g of x plus h. So let's take that x plus h and plug it into the function in place of x. And let's simplify that expression. Someone square this out for me. What do you get when you square out x plus h? Thank you. X squared plus 2xh plus h squared. Boy, it's convenient just to be able to square that out. Now here, we're going to distribute the negative sign, so minus x minus h. Are there any like terms that I can cancel or anything like that? No. So, all right. Let's move on to the second part, calculating delta y. For delta y, I want g of x plus h minus g of x. So what we just calculated minus the original function. So that's x squared plus 2xh plus h squared minus x minus h minus the original function, x squared minus x. When you're doing these things with polynomial functions like this, that g of x term or f of x term, depending on what you're calling it, should completely cancel itself out. So if you distributed that negative sign, I'd have a negative x squared. Negative x squared is going to cancel with positive x squared. Likewise, distributing the negative sign makes that a positive x, which will cancel with negative x. So g of x completely cancels itself out in polynomials like this. That leaves me with 2xh plus h squared minus h. Okay. 2 down, 2 to go. Let's calculate delta y over h, which is basically this divided by h, and then we'll simplify it. Factor out the h from the numerator. It's h times 2x plus h minus 1 over h. We get some nice cancellation here. The h's cancel out, and it leaves us with a relatively simple function, 2x plus h minus 1. What's the last step? Yep, take the limit. So the limit as h approaches 0 of delta y over h, which is really the limit of this, 2x plus h minus 1. What's that limit going to equal? 2x minus 1. And that's your derivative function. That's your f prime. This tells you a lot about your function. This tells you the slope of the tangent line. So in particular, the problem asks you to find the slope of the tangent line at c equal 1. Before we do that, are you okay with this calculation? All right, so let's find the slope of the tangent line. In fact, let's find the equation of the tangent line at c equal 1. First thing we need is the slope. So f prime of 1, what's f prime of 1 going to equal?
1.
Yeah, f prime of 1 is going to be 1. 2 times 1 minus 1 is 1. To find the equation of a line, I need two things. I need a slope and an intercept, or I need a slope and a point. In this case, I think we'd be best off just trying to get a slope and a point. So we've got our slope. That's the slope of the tangent line. But what's the point? What are the coordinates of the point that I should use? Yeah. Plug it back in to the original function, g of x. And I call this f prime. I should probably have called it g prime. My bad. So g prime and g prime. Yeah, but you want to plug back into the original function. So g of 1 would be 1 squared minus 1, which is 0. Okay. So our point then is going to have coordinates of 1 and 0. And the slope of our tangent line is going to be also a 1. It's going to be a pretty simple equation here. Y minus y1 equals m times x minus x1 is going to be y minus 0 equals 1 times x minus 1. If you distribute and simplify, we're just going to get y equals x minus 1. That's the equation of your tangent line. One of the goals I have for you, and we're going to do a lot of this stuff, is find the equation of the tangent line. See how your function is changing. Let's confirm this by looking at our graphs. So I asked you all to get graphing calculators, so we'll do it there. Let's do it on our graphing calculator. So I'm going to plug in, first of all, my function, which was x squared minus x. And then I'm going to plug in the equation of the tangent line, which is x minus 1. Now the point at which this graph should touch, or the tangent line should touch the graph, should be at x equal 1. So I want x equal to 1 to be in the center of all the action. So let me set up my window between, say, -1 and, I'm going to go up to 2. So -1 to 2 on the x-axis. And then I'll let the calculator do the rest by pressing zoom and then 0. Okay. Looks pretty good. You can kind of verify things a little bit. If you hit the trace key, it'll put a cursor on your calculator. And you can kind of move around over here. And, depending on how lucky you get, you might get close to 1. Now, look in the upper left-hand corner. It's telling me I'm on the first of my two functions. I'm on y1, and the coordinates are 1 and 0. If I hit the down arrow key, now I'm on y2, But notice I have the same coordinates, 1 and 0. So that point is on both graphs. So that's kind of reassuring. It should be on both graphs. Are you comfortable with our work on problem number 66? Because there's a little bit more I want to discuss about this problem. So before we move on, we good there? Let's look back at the derivative function. And remember that the derivative tells us some stuff about the function. So g prime of x was 2x minus 1. That tells you the slope of the tangent line. Now looking at this graph, at some point you've got a horizontal tangent line. Looks like the graph is going to have a tangent line that's nice and completely horizontal, just like my pen here. So where would that be? It's a good question. Well, what's the slope of a line that's horizontal? 0. So what you can do then is set this equal to 0 and find where that line is, where that tangent line is horizontal. So 2x equals 1, x equals 1/2. And at x equals 1/2, you should have a horizontal tangent line. In fact, if we trace here at 0.5, wrong function. There we go. 0.5 looks like the point where that parabola kind of turns around and starts going up. So in that moment, when it changes from a decreasing function to an increasing function, you've got a horizontal tangent line. Like I said, keep in mind that the derivative tells you how the graph of the function is changing. To the left of this point, what kind of slope will we get for a tangent line? Well, it should be negative. To the right of this point, slope of the tangent line should be positive. And here's your break-even point, where the tangent line changes from a negative slope to a positive slope. Those points where the derivative is equal to 0 are going to become increasingly important. All right, for now, what I'm trying to do is build a connection between the graph of a function and the graph of, the function and its derivative graphically. We're going to do a little bit more of that. Any final comments on problem 66 here? Let's take a look at some of the problems in the book. Yeah, please. I tend not to give huge problems because, you know, if you make a mistake in one part, it tends to carry through on the rest. And I want to give you the best opportunity that I can to show me that you know what you're doing. And, you know, I don't want to see you make a tiny mistake that costs you big later on. So I try and make my problems a little bit smaller. What you should expect from me is one problem like this, where you calculate the derivative of a function based on this limit definition. Okay. Just one. Because soon enough, section 3.2, we're going to start learning formulas that's going to make this so much faster. But it's important to keep this in mind because there are things that can go wrong in this limit process. And understanding that limit process can help you understand what can go wrong and where the derivative can fail to exist. That's something we're going to discuss today. So, yeah, thank you. So let's take a look at problem number 39. Actually 39, 40, and 42. Look at all of those. If I can manage to get that up on my screen. All right, let's keep it there and try not to breathe. Problem 39, 40, and 42, they're giving you the graph of a function. And what they want you to do is to try and figure out what the graph of the derivative would look like. Sketch the graph of the derivative. And let's see, I'm not sure I get enough room on this, so here we go. Jeff Unchained. Just have to talk loud and hopefully it works. Well, let me. Does this one work? Yeah. Let's think about the derivative for each of these functions, starting with number 39. The derivative talks about how the function is going to change. As you move from left to right, how is that function changing? Well, in 39, what's the change like? Yeah. All right. It's kind of a steady change, right? As you move left to right, the change is whatever the slope of that line is. Looking at that, it looks like the line y equals x. So as you move to the right 2 spaces, you move up 2 spaces. So you get a slope of 1. So that looks like how the line is changing, or how the function is changing. If you were to calculate the derivative would be just that. You'd have a horizontal line at y equals 1, because that's how the function is changing. It's a constant rate of change. No matter where you're at, the rate of change is just the slope. Let's move over to problem number 40. Is there a lot of change in the function for problem number 40? No. It's just, is the function changing at all? No, it's the same. It's constant. So the derivative function here would be a horizontal line right at 0. Because there's no change in this function. It's constant no matter where you're at. So let's move down to 42 then. See if I can zoom in a little bit on that. 42, there is some change, right? In fact, the change changes at a point, right? So as you're coming close to 4 from the left, what's happening to the function? Is it decreasing or increasing? What's happening to the function? Decreasing. But it's decreasing at a steady rate, correct? It's decreasing at a constant rate. So the derivative here would be a line with a negative value. So at negative 1 here, y equals negative 1, up until we got to this point, to that corner point. Then what happens? To the right of that point, what's going to go on? Yeah, it's going to be positive. Because to the right of this point, the function is increasing. The derivative describes how the function is changing. So it's changing in a negative way to the left of 4 and in a positive way to the right of 4 at a constant rate both times. Now I said earlier that one of the things that I want you to get from working with the definition of your of the derivative is an understanding of what can go wrong. So let's take a look at some of the things that can go wrong when you're looking at the derivative of a function near a point. So 3 things that can go wrong zoom out a little bit. While trying to find f prime of a. So you're trying to find the derivative of a function at a particular point. And there's three things that can go wrong that I want you to be aware of. Three kind of general things. Let's keep in mind that the derivative is calculated from this limit. The limit as h approaches 0 of f of x plus h minus f of x over h. That's our derivative function. Typically speaking, you won't see it written like this in a book. In a book, instead of h, has anyone figured out what they use? Delta x. I don't know, what do you like better, h or delta x? H, yeah. Seems a little bit more user-friendly. So I typically go with h as much as possible. So, but the derivative is based on a limit. And there are things that can go wrong with limits. We saw some of that earlier. In order for a limit to exist, what two things have to be equal? Good. The limit from the left and the limit from the right have to be equal. And that's not going to be true if you don't have a continuous function. So one thing that can go wrong is that the function is not continuous at x equal a. So f of x is not continuous at x equal a. So that's one thing that can go wrong. What else can go wrong? Well, f of x has a corner point. And here I'm being a little bit informal with you. Corner point is just a point on the graph that is sharp. It's the point on the absolute value. It's the vertex of the absolute value. It's not the vertex of y equals x squared. That's nice and smooth. But if you have a corner point on your graph, then when you start trying to calculate this limit at that corner point, and let's look back at problem number 42 real quick. The limit from the left and the limit from the right, well, the slope of the tangent line is going to be different depending on which direction you're coming from. One way it's going to be -1, the other way it's going to be +1. The bottom line is that that limit is not going to exist for such a corner point. Now there's one other thing that can go wrong, and that is when you're trying to find the equation of a tangent line could be vertical. What kind of a slope does a vertical line have? Undefined. So f of x has a vertical tangent. And I'll give you a warning. A lot of times when I ask this question on an exam, you know, what can go wrong with a function, why it won't have a derivative at some point, people get confused and say f of x has a vertical asymptote. Well, yeah, okay, but that's really part A, or the first one. F of x having a vertical asymptote means that it's not continuous there, and that's fine. But that's different than having a vertical tangent. And we'll take a look at some examples there. So there's three different things that can go wrong when you're trying to look at a function and try and figure out where it might or might not have a derivative. Let's try and spot some of these as we look at some of our own examples. We'll start with problem number 76. 76 and 78. So we're trying to find the values of x at which f is not differentiable. So the problem described in the book is actually we're finding where it is differentiable. I think it's easier just to list the ones where it's not differentiable. So take a look at that for a second, and then we'll see what you think. How about the first one, problem 76? Where's that not differentiable? Yeah, plus and minus 3, because you've got corner points here. You should be able to see that the graph has these sharp points. And when that's true, your function's not going to be differentiable. So x is plus or minus 3. How about problem 78? Where are we going to run into issues there? At plus or minus 2. Now, what's the reason that we have issues there? It's not continuous. Thank you. The function's not continuous. So at plus or minus 2, the function's not differentiable. Everywhere else, we're okay. It's just those 2 points. Let's move down to problem number 80. How are we doing on that one? Is that one differentiable everywhere? Yeah. At x equals 0, what's going on there? Is it continuous at 0? No. If it's not continuous, it's not going to be differentiable. Period. So we saw a couple examples of some of the things that can go wrong. Let me show you the third one, because we haven't seen an example of that. And for that, I'm going to cut over to Desmos. Let's see, right here. Let's take a look at the graph of y equals, let's see, the cube root of x minus 2. Now I'm going to write the cube root as something raised to the 1/3 power. I'm not sure where the cube root is on this one. And then let's add 4 to it, just for giggles, just to move it away from the axes. Can you see a spot where this function is going to have a vertical tangent, where the tangent line is going to be straight up and down? Yeah, at x equal 2, the tangent line would be vertical. And that's okay to have a vertical tangent line, it's just the vertical tangent line has an undefined slope. So there's no slope, no defined slope here. So that's another place where a function can fail to have a derivative. Let's do 2 more here in terms of a couple examples. And these next 2 are piecewise functions. So, I'm not sure I want to, I don't know. It's up to you. Do you want to learn how to do piecewise functions on a graphing calculator, or doesn't matter? Yeah? Okay. All right. So let's take a look at problem number 84. Now it's cool that you can learn something new about your graphing calculator. I'm happy about that, but graphing piecewise functions is a bonus. There is something a little bit later that I will require you to know, and that is how to find x-intercepts using your graphing calculator. This is a bonus. If you can get this, that's great. So 84 asks us to look at the function f of x, and it has 2 parts. X cubed minus 3x squared plus 3x. That's assuming that x is less than or equal to 1. And then another function, x squared minus 2x for x greater than 1. Now there's a couple ways we can put this into our graphing calculators. I'm going to try and be pretty simple about it. And I'm not sure how much detail I want to give you, so let me just be as simple as I can. Into y1, let's put this first part of the function. Use a left parenthesis. Let's put that whole piece in parentheses. So x raised to the third power minus 3x squared plus 3x. But I don't want that for all values of x, do I? I just want that for values of x that are less than or equal to 1. Now, you can do a times or you can do a divide. Let me suggest you just do division by, and now we're going to put it on our condition. I want to type in x is less than or equal to 1. So type the x. And now the question is, well, where on earth do I find the less than or equal to? And you find that right above the math key. You hit the second button and then the math key. If you read there, it says test. And now you have all your choices. So we want less than or equal to, so you can type number 6 or scroll down and press enter. So x is less than or equal to 1. Let's repeat that for the other part of our piecewise function. So again, parentheses, and then x squared minus 2x. Now up here I did division. You don't really have to do division. Maybe when I graph it, I'll explain why. You can just do it times. I recommend division, but you can do it times. And this time we want x is greater than 1. So go back to your test, type in a 1, like that. Both of these are polynomials. So you know what? This should be a 2x here. Let me go back and fix it. There should be a 2x inside there. Both of these are polynomials. So left to themselves, they'd be continuous differentiable functions, because polynomials are nice and smooth everywhere. You're not going to have any corner points. You're not going to have any vertical tangents, and they're continuous. The question is, how well do they line up? Do these match each other, and do they do so in a nice, smooth way? Before I graph it, are you able to get that entered? Because I don't want anyone that's not keeping up. So before we go on, are we all okay? Are we okay with that? All right. Where might we run into a problem with this function? Yes, at x equal 1. So whatever the window is that we choose, let's put 1 in the center of our window. So, I don't know, we can go from, say, -1 to 3. Sure. All right, -1 to 3. But 1 should be kind of in the center of our window. Let's see. Let's hit zoom and then 0. Let's see what our graph looks like. So what that test condition does, that x is less than or equal to 1 or x is greater than 1, is it's like multiplying by either a 0 or a 1. So when this is true, it has a value of a 1. So it's like multiplying by 1. When it's 0, or when it's false, then you get a 0. So you're either going to graph this function or 0. And you can see that here, right, with the red. So here to the left of 1, it's 0. To the right, it's 1. You know, it's just a function. But if you take a look at what we did with the blue function, what's nice here is that when this is false, what's happening? You're going to divide by 0, right? In which case the function's undefined. So really I only see the graph where it's defined. So it's a little trick. If I go back here and make that a division, then the graph's just going to look a little bit better. All right. Is this function differentiable everywhere? No. Where are we going to run into problems? At x equal 1, right? Because the function is not continuous. So that's it. That was the point of this problem, is to figure out if and where the function was differentiable. And it's not differentiable at x equal 1. So f of x is not differentiable at x equal 1. All right. Let's try that again with one more function. That's going to be problem number 90. Any other thoughts or comments on 84? Problem number 90 looks like this. F of x is 1/2 x plus 1. And that's for x less than 2. And the other function is the square root of 2 times x for x greater than or equal to 2. So see if you can't graph this function much in the same way we did problem number 84. See how they line up. For the window on this one, I'm going to suggest, say, 0 to 4, because that puts x equal 2 at the center of things. So 0 to 4. And then from there, zoom 0. Everyone able to get a graph that looks like this? Helen?
Yep.
Yeah, looking good. So what do you think? First of all, is this graph continuous at x equal 2? Yeah, absolutely. You can plug in x equal 2 into both of these functions. You're going to get the same thing. You get y equals 2. Is it differentiable here? What do you think? Is that a nice... Do those line up pretty smoothly? I know there's a little bit of hole, but that's just an artifact of our graphing calculator. It's not really there as part of the graph. Do those line up smoothly? Is that a corner point? No, it looks pretty smooth to me. At least I'm not going to try and trick you with something like this. If it looks smooth, it's going to be smooth. So this is differentiable everywhere. So f prime of x exists for all values of x. Or on the range of negative infinity to infinity. And I think I showed you guys the fancy math notation for that, right? Script R. Basically means negative infinity to infinity. Was it worth it to learn a little trick about graphing piecewise functions? A cool one? All right, good deal. Liv, if I may, give me some more feedback. Did you like the extra little bit about the dividing? Okay. All right. Cool. Well, thanks. I think we're pretty set on section 3.1. I'm glad we had some extra time to go over that. Yeah, question. I've thought about it. There's a ton there, but you know what? If you pay good attention to this class, you're going to learn a lot. So, actually, coming up, we're going to learn some more too. So, yeah. All right. For homework, now some of this, theoretically, some of this was already done. But if not, then okay. This is on page 123. Try 1 through 17, 25, 33, and 34. Of course, 34 we did in class. Typically, these are just the odds. 41, 55, 75 through 79. No, 75 through 89. Now let's just make that 75 through 89. So these are just the odds with that exception. And that's section 3.1.